And then we'll see different applications like spelling correction application in using the language model, and also uh, that word similarity problem with word to vec embeddings. Okay, so that will be done, and then we'll also see different applications like sentiment analysis, word similarity analysis, and we'll also see the implementation from scratch of these algorithms. We'll also see the implementation using GenSim library, but we also implement them from scratch so that you will get more in-depth understanding of the algorithms. Okay, so I will start with the first experiment, which is a language modeling model using n-gram models. Okay, so if you will remember from the lab in the morning, uh, sorry. So in this lab, in this experiment, what we are doing is we are implementing trigram language model and Laplacian smoothing technique. So if you remember that trigram language model basically works on predicting the next word based on previous two words, and Laplace smoothing is used to avoid the situation of like coming probability to be zero. So that implementation will see, and then we'll based on that we'll try to see that what is the next word which we can predict, and the model will be based on the Brown corpus, which we'll use as a training corpus basically. So from this Brown corpus we'll try to estimate the probability of the next word given the previous two words. So that is the experiment that we are going to do. So firstly, we import NLTK and download this API for using the different functions of NLTK. NLP, this is an NLP library in which we use different functions of it. Okay, so we start with this, and in the first, we directly take all the sentences from the Brown corpus and make all the words in the sentences as in the lowercase. Okay, and then we do some kind of pre-processing. The pre-processing, we add the start token and end token in the start and end of the sentences, so that we'll know, okay, this is the end of the sentence and the starting of the sentences. So for example, if the way you start with the first sentence, so there will, for this example, for the first word, the two previous words will be two start tokens. So that is why we start with the two s start tokens. So for the first word, if you want to predict the first word, because there is no context in between, so to give the model idea that this is the first word, and there are two start tokens here, and in the end, okay. And then we count the frequencies of unigram, bigram, and trigram. And we based on the corpus of all the words, we just keep it ready for because if you remember that we have to predict the next word based on the count, and based on the how many times a particular unigram, bigram, or trigrams are appearing, and based on that we basically estimate the likelihood of a word which will be coming next. Okay, so now this is the code where we basically build the trigram model, in which firstly we calculate all the words. Okay, what is the probability of them, and then the context words. So bigram count.cat means W1 and W2 is basically the context words, and based on that we compute the probability of the next word, but W3. So this is just directly implementing the formula which we have already know. And then this is a math implementation for the Laplacian smoothing, in which we add 1 in the numerator, and then plus v on the vocab size in the denominator. Okay, so and then we get the probability for the word 3. And then this is a function where we basically predict the next word based on what we have seen, two words. Okay, and then we return. Okay, so if I run this, if I run this, so I'm taking examples like the United. So given these two words based on the corpus, I'm printing 5 top probable words. So that way, that we can see that what is the next word based on the corpus. So we can see that the states, the United States is the highest probable word that should come next, and which is quite correct also, that the next word may be that states. Nations can also be there, but yeah, states based on the corpus, it is more probable. For next example, it is not. So based on the corpus, it is like after the it is. So based on the corpus, not is the highest probable word, and A is also almost very similar probable word for the next. Okay, so the implementation of language model is very straightforward. Based on the problem, we can use it for different n-gram models. Okay, so this is again the same implementation, but we have some more examples which I have shown, like the president of, this is for new test samples in which we have the president of. So based on the words president of, what is the most probable next word is the, is a good. Okay, so to get more accurate and more realistic outputs, we should have more bigger, corpus, training corpus. Brown corpus is also good enough, but if you want to use it for really, you want it to be work really well, you have to use bigger data sets. And this is the like better implementation. That it's the same thing, but we have implemented to make it more, that interactive function. And we have used Reuters database instead of having the Brown data. So just to see that if we change the data, what is the predictions we get? Basically, that will always, as it is intuitive, it will change based on the that the corpus. So because we are just estimating the likelihood of the words based on the corpus. So this is like if I write some word, let's say I write I, so it will just give the next word. If the starting word is I, so it is based on the data, it is showing the next word should be thing, which is more probable. So if I write, let's say think, so now it will predict based on the next word I think. So it is like it. So I just write it. Okay, it means it is saying it's like it's. So I just write it's. So again, it is suggesting to type A. I type A and then vary. So it is based on the sentences. It is giving options based on the previous words. So it is suggesting healthy. So I just write healthy, development, and then comma. And then, so it is based on the data. Let's say I just take some other options. Let's say I take and then it is suggesting some feasibility. And now let's say I just now stop here by, okay, now it will stop when I press full stop. So it is showing that I think it's a very healthy development and feasibility studies by 1990s. So you can observe here, this is that language model, like a trigram language model, is not very efficient, but it is somehow taking some grammar and some limited syntactic information intact, but it is not very useful in the real world problems, because now we have a lot of advanced models in hand, like based on the neural language model based methods, models, and also large language models. But still, this is also interesting to learn. probabilistic language models, which is very fast. If you have very small data and sorry, it's a small problem and you want it to be worked like very fast, you can think about using it. Okay. So this is a simple demonstration of next word prediction using trigram language model and with the Laplacian smoothing. Okay, so now if you have any doubt or questions on this, please let me know. Otherwise, I will go to the next uh, experiment. I'm just sharing this in the chat box so that if you want, you can also experiment and run the code in your own system, and you can ask if you have any questions on it. So in order to share on the chat, I have to disconnect it. Okay. Okay, so if you don't have any questions, so I'll quickly move to the next experiment. Is there any question? No, okay. So in this experiment, we have seen that language modeling can also be used for spelling correction. And I prepared this experiment in which we are using language models to detect the spelling mistakes. Okay. So for this, what we are doing is uh, given any word, okay, given any word, what we'll do is we some with the help of edit distance algorithm, we generate different variations of the words, and then we compute the probability of availability of that particular word in the corpus using the language model. And then if misspelled word is there, so the language model will give its probability to be very low. Okay, so that is the idea. So the idea is language models can be used for spelling mistakes detection because it will give very low score to the misspelled words. So that is the idea, and which is quite efficient in if given good vocab based corpus. Okay, so that if you need, you can always use spelling mistake detection, and you can use language modeling for that. Okay. So again, we start with NLTK library, and then this IPY widgets is for interactive interaction with the user. Okay, so and all other uh, related libraries. Yeah. So in this also, we are using Brown corpus. We are doing the pre-processing and counting unigram and bigram language models. Uh, so it is similar to the code which we have seen in the previous. Now this is the language model and correction functions. So firstly, this function is for computing the unigram probabilities and also having Laplacian smoothing in this. And this is the function where we are computing the probabilities for the bigrams, like bigram language model with Laplacian smoothing. Okay. And now this is the function for edit distance. So edit distance function basically gives different variations of a given word. So based on this algorithm, which is quite a standard algorithm for this spelling correction method. So we can correct the spellings, and we can also find out the different variations of the word, okay, by doing splits, deletes, transpose, replaces, and other operations, we can do that. And this is a function to find out if a given word is present into the vocabulary or not. And this is a function for generating the candidate sentences. So given any word, what are the different variations? We just call the edit function for this and see what are the available options and different variation of a given word. So for example, if let's say a word receive is there, but their spelling is mistake. So edit distance will give all the options, and then we'll see all the options and see the probability of this using the language model, and probably the best word or the correct spelled word will have highest probability. So that is the idea. So this is this is a function where we do this kind of operations, in which firstly generate the candidate words, and we see all the context, all the words, if there is a context given to us. So we'll use a bigram language model for that, and we compute the score. And if the context word is not given, then we'll use the unigram language model and then find out the probability of that word. So given any word and the context, so if context is given, so it is better to get the correct spelling word. Okay. Now this is, just run this. Now I'm running this. This is a interactive input widget in which I'm just calling the function and taking the input. Okay, so now let's say we write word receive. Okay, so which is I made it a wrong spelling. So since this word is not present in the vocab, possibly because of spelling mistake, and it is suggesting the correct word for this. So that is receive, because it has got like highest probability. Okay. So all these options were generated using the edit distance, and then we could find out that with the help of language modeling that, okay, this is a misspelled word, and the correct meaning can be, that receive this one. Let's say, let's try another word, government. Government, it's not present. Maybe the correct word is also not present in the. Yeah, so government itself is not there, but okay, let's see, try another one. Kin is also not present. Okay, sorry, it is in the library. So if I write KINF, so which I did the spelling mistake, so it is suggesting kind to be correct word, and king is also there, but the kind is having higher probability. Okay. So it was is more probable. Okay, so you just try and see if it is working for you or not. Okay. So this is again a small experiment for understanding that how we can use language modeling for spelling correction, spelling mistake detection, and then we can use it for correction using the edit distance algorithm. Okay. So any questions on this so far? Now I'll write the link for this notebook also. If you wish, you can also run this in your system. Sorry, okay, you got the link for the second experiment. Now I will share the third experiment. You're not, I'm not audible. Hello?
Yes, it is audible, but for
Not
just
audible.
1 minute, you are
Hello?
not audible. Now you are audible, sir.
Yeah, even
Hello?
I think you are not audible.
Well, actually, there is an issue in this, I think.
Okay, so now we go uh, to the next experiment in which we have developed the code for finding out the embeddings of different words in the corpus. Okay, so if you remember, we have discussed this in the theory in the morning that there are mostly three algorithms, which is quite foundational way of developing the embedding models. And first is continuous bag of word, another is skip gram, and third one is the variant of the skip gram, which is skip gram with negative sampling. So continuous bag of word and skip gram models are basically works in two ways. Like firstly, we find out the input and output pairs for SIBO. We find out the predict the context was given the target word, and in the skip gram it is the reverse. And in negative sampling method, we try to convert the problem is a binary classification problem in which we create the data sets and generate the data, positive samples and negative samples, which is basically the context word and the target word as a positive samples, and non-contextual words with the target word as negative samples. So, and based on this, we just train the neural network, one layer neural network in case of SIBO, and skipgram, and we use logistic regression in case of skipgram with negative sampling. And for this implementation, GenSim is a very popular library, which is kind of, very state of the art implementation for word2vec, which is very efficient. And if you want to use word2vec, you can directly use. And otherwise, if you wish, you can also write the code from scratch, which is also, as you will see that also in the later session, later on in this session. Okay, so for this, we just install the GenSim, pip install GenSim and NLTK. I'm not running this code because to run this on big data, like it will take a lot of time, but okay, so I just show you the things here, which is already have all the outputs like available to us, so that we, if we wish, we can just experiment with different inputs also. Okay. In the meantime, maybe I just run it so that we'll have some more. Okay, so in the first section of the code, first we just import the GenSim and the word-to-vec model from the GenSim. Okay, and we also use PCA for just for the representation of the embeddings which we have learned to transform it into a low dimension and then visualize it using the PCA so that we can see the see that what is the semantic similarity which we talked in the theory. Are we really able to learn those kind of semantic similarity or semantic information in the word embeddings that we'll see. Okay, so for this, I've used text 8 data, which is not very big, but it is sufficient for demonstrating purpose for this code because it takes a lot of time while to just train these kind of models sometimes because it is given a corpus, we first find out the input output pairs and then we train the model and you can visualize that creating multiple input output pairs from the large corpus, it will be like a lot of samples. So the training data is quite becomes quite big if you have good like sufficient significantly large corpus. So that is why I've just taken this. Okay. Now I've taken some words just to see their embeddings and the visualization to understand if we could really like learn the semantic information embedded into the embeddings for these words. We can take any words from the corpus, but I've just randomly took these words to see what their visualization. Okay, so and we could also see that if we could really like infer the inferences from king, queen, and man, women relationship, analogy relationship. Okay. So in GenSim implementation for word2vec, there are mostly five functions, five to six parameters, and the function is here. You can see SIBO, and it is like word2vec. The first parameter is the sentences. It means you just give the data to this this word2vec function, and next is the word vector size. Vector size is 100, means I want to learn the representation of each word to be 100. Okay, and that is 100. Now this is window parameter. Window parameter is how much context size I want to take from left and right for a given target word. Okay. Minimum count is a parameter which we use to just eliminate the words which are not frequent. So the words which are occurring less than 10 times will be just ignored. Okay, because that is like will not be able to learn the good representations for those words which are not frequent. They will their embeddings will not be their weights will not be updated as such, like, so that is not good representation, so that we can remove. And worker is just the computation part, like how many parallel threads can be used for this. And this is very important parameter, that is SG. So SG means this is a parameter which tells word2vec that what implementation of the algorithm you want to use. So by default, this SG is equals to 0. It means this is the implementation of the SIBO. So word2vec itself will take, that SIBO, continuous bag of word implementation. And if it take it like 1, so it will take a skip gram. So with this parameter, this implementation, GenSim implementation, we automatically understand, okay, this has to be trained using continuous bag of word or skip gram algorithm. Okay, so so when I use the SG is equal to 1, so this will develop a skip gram model. And third one, the implementation is for skip graph with negative sampling, in which we just pass one more parameter to this, and which is like negative sampling. So by giving parameter negative is equals to 5, it means it will take 5 negative samples corresponding to each positive sample. So that is the parameter which we can give to the model. So this will automatically create positive samples as we discussed. And for each positive sample, it will create 5 negative samples by taking the target word and non-contextual words. So by this, it will just create input output pair and then implement the skip gram with negative sampling. Okay. Now I run all these models with different parameters, like by changing the window size to 5, then 2, and then also skip gram with 2 and 5, and then skip gram and SGNS skip gram with negative sampling with window size 5. Okay, so I've just changed a little bit of the window size just to see if that makes any difference or not. And then I will see that what is the output we'll get. This is the function for plotting the 100-dimensional embeddings to 2 dimensions and then plotting it. Okay, so what we're basically doing is like for each word, which is a 100-dimensional word, we use PCA to transform it into 2 dimensions so that we can visualize. Otherwise, we cannot visualize 100-dimensional vectors. So sometimes by doing this, some information might lose just actually what has been learned, but somehow this transformation gives a very good idea of what kind of semantic relationships are present in the embeddings which we have learned. Okay. And I just plotted the heat map for the similarity, cosine similarity of different words. Okay, now let's see the results. Okay. Now this is first model in which we used a skip gram with negative sampling and the window size 5. And you can see that the words, the target words, sample words, which we have taken to observe their relationship and that semantic information which they carry. And we can see that given the small corpus, even though the words are quite good, see that relation between men and women, you can see that there is a relation there, and the similar kind of relation is there between king and queen. Okay. And bus is far from city and village as compared to city and village is quite closer as compared to the car, and the road is also on that side. It is not perfect, but yeah, so the words which we have chosen, it is showing quite uh, good results. Okay. Now again here, king and queen, men and women. This is not that good because you can see that there is a relation between king and queen is slightly different. Here the relation is like if you draw a vector from man to woman and king to queen, so it is not that parallel or not that similar. But yeah, apart from that, we can see that the representation is quite close, like for king and queen, and men, women, and child are also very close to each other. City and village is also close to each other. Car and bus they are not close, but they should be slightly closer. But yeah, somehow it is also a lot of information we can visualize in this. And when we increase the context size, so you can see it is slightly quite close, but yeah, not that impact on which I can observe. But sometimes when we increase the window size, so more information sometimes semantically more in contextual information is there, more information with respect to the semantics will be included. But probably for these examples and embeddings, probably the difference is not that visible. Okay. And this is the implementation of the skip gram with window size 2. And here we can see that relation between man, women, child. All the models are basically able to club men, women, and child closer, king, queen to closer, city and village to closer, and apart from other words, bus and road and car, they are like could not be. They are not that close to each other, but. And here, skip gram with 5 window, I think this is the best model probably, or we'll see the SGNS also, that is also quite good. So what I observe here is like a relation between king and queen is very, very nicely represented here. So if you see, if you draw a vector from man to women and king to queen, they are very parallel and very nicely, nicely the relation between king and queen and man and women are being captured. And city and village is also quite good, bus, road and car. Bus and car are far, maybe that should be the closer one, but apart from that, the relation between these king queen analogy is quite nicely captured. Okay. So the point here is like we have different algorithms based on the large amount of the data. If you use it's a skip gram with negative sampling, which is the most popular model of using the word to vec, and you can try with different window size, that is a parameter. You can just see with different analogical things to experiment with the performance of the embeddings and like use it for your application. Okay. And this is just a heat map. You can see the changes between the cosine similarity of different words, which we have already seen that in that which was visible, but that was on a two-dimensional part, which a lot of information was lost in that particular thing. But here we can actually calculate and see that what is the cosine similarity between two words. Like you can see, queen and king is very close, and king and sorry, men and women is also very close, 0.7. Women and women is one. Women and child is also very high value, and so on. Okay. And similarly here, so in the here in the PCA visualization, we have already seen that similarity between different words. You can also analyze it later on when you'll run this code by yourself, and then observe that for your data, okay, are you really able to learn the semantic information in the embeddings? Okay, so your embeddings are like capturing semantic information. Now I just run different words randomly on a model and try to find out what are the similar words. So I just gave some words like fruit. So it is giving my most similar words as fruits, juices, vegetables, flowers, and so on. And for the words car, it is giving me car, automobile, driver, truck, which is quite good. Okay, and then I gave, sorry, I just could not change in the title which is printed, but here I'm giving third word as input is run, which gives the most similar and close words as running, runs, ran. Okay, so three words are quite close. And then booted, tasking, and a lot. Okay. And with the skip gram model and the SIBO model for king word, you can see that prince, hakun, I don't know what is this, but throne is quite close. And prince, queen, throne, emperor, this is giving quite good results, SIBO. Okay, this is the same model. Okay, here I just plotted the relation between the India and Delhi. Delhi, oh, okay, the Delhi is not there, but you can see that the country India and Italy is very close. Paris is a city which is also very close. Okay, here men and women is there. Actually, I think this was the script was stopped in between. That is why it is giving stopped. Okay. Now I just see if, okay, it's not running. Uh, yes, yeah, here it could run. So see, men, women, and child are very close. King, queen, village, road. Okay, this same simple words here also not there. Yeah, here. So this is the result when I try to see the impact or the analogy for men, king, and women and king. Yeah. So and Paris, France, Italy. So when I run these models for the SIBO model with two context size, you can see that it gives a man minus king plus women. So this is a vector. One vector embedding vector of man is subtracted from embedding is subtracted with king, embedding vector of king, and then added embedding vector of for W women. So that will be very close to the word vector of the queen. And similarly, all the analogies is being plotted, and we can observe that for the first analogy, almost all the models could give good results, except this skipgram model, which is giving some random value. And for almost all the model, uh, uh, like for this Paris, France, and Italy experiment analogy, mostly everyone is not giving good result for this data set. Okay, so given by increasing the data, so you can see that all the analogies and the semantic information will be represented or will be learned in a better. So anyone, if you have any questions so far, please let me know.
If anyone has any question, you can
I'm
write in the chat box.
Yes, I am placing, I mean, in the chat box, I have given the link, shared link for the collab, which we have just shared. Okay. If you wish, you can just run in your system and then experiment and visualize and see that what is the output we get. Now I will request Pooja to further explain the implementation from scratch for skipgram and different word-to-vec models like SIBO, skipgram, and applications on sentiment analysis and other things. Pooja, can you share?
Yes, sir. Pooja will share. And thank you so much, sir, for the implementation information you have given on the
Yes.
word embedding and schemagram topics. So thank you so much.
So I'm here, Rinki, no
Now,
problem. So we together will be discussing.
okay,
Okay. So after that,
okay, sir.
yeah. So
Okay.
Pooja, please share.
So good evening, sir.
Yes, Pooja, please share. Everyone, please let us know if you have any questions, anyone, or maybe we can just take a 2 minutes pause and you can just see and observe that code which I have shared with you all. And then within 1 or 2 minutes, we can start. Pooja, I think we can start.
Yeah, okay, sir. So, welcome everyone again to the hands-on session on language modeling and embedding. As you have already seen the formation of word-to-vec model covering both the SIBO and skipgram architecture using Genzim library. So, in this session, we built a word-to-vec model from scratch, which will cover both the SIBO and the skipgram model. So in order to do that, we will use the Brown corpus text data, which consists approximately 57,000 of text sentences. So in this session, we will see how to generate the dataset pair, the context and target pair for SIBO and skipgram, both the architectures. And we will see their training on the above defined dataset. And then we will see a use case by predicting the closest word to a given word. So let us start with the session. So we will start by importing all the necessary libraries. The first one is Natural Language Toolkit, which one is definitely required library for every NLP task. From the library, we import the data set, the Brown corpus that we are using. So before starting with any process or any coding program, we first pre-process our data set. So here also we have cleaned our data set by converting each word into a lowercase alphabet. This will automatically remove all the non-alphabetic characters. So we store our total length of clean sentences, and in order to see that how the sample look like, we printed some samples. Here printed 50 sentences from the data set. So the output for this code is as follows. After cleaning, we are left with 56,766 sentences, and the first 50 sentences of the data set looks like this. Now, after data pre-processing, we will build the vocabulary and word code encoded vector for each word in the dataset. For this purpose, we will use two main functions, word to IDX. This function assigns index to every word of the vocabulary. And the second word is IDX to word, which is the reverse function, which will assign word given any index. In this vocabulary, we do all the pre-processed sentences. We map each word in the vocabulary by word idea. We will assign the figure ID word of the vocabulary. Find the reverse function ID word, which will be used during the coding process.
Pooja, I think your voice is quite become low suddenly. Can you please check your voice?
You are not audible.
We will now create a one hot encoded vector. So am I audible to all?
Yeah, now it is better. Suddenly your voice became like low. So now it is better. Okay.
Okay, sir. So I will repeat this part again. So as we have pre-processed our data, so we will build the vocabulary and we will generate one hot encoded vector for each word in our vocabulary. So here we start with the pre-processed data. Every word an integer ID using the function word to IDX, and we also define a reverse function IDX to word, which will be used during the decoding process. Here we have printed the length of our vocabulary, and after defining the vocabulary, we will construct one hot encoded vector using the identity matrix So for that, first we import our library NumPy as NP. The one-hot encoded vector is constructed as by using the identity matrix of size, vocabulary size, cross vocabulary size. So here we print our output as the vocabulary size after. Actually, vocabulary is what? The number of unique words in our vocabulary. So as we have already seen that we are left with 56,766 sentences after pre-processing the data. So in those sentences, how many unique words are there? That will be considered as our vocabulary. So we print our vocabulary size, that comes to be 40,234. We also print first 100 indexed word. The output is shown as the word A is assigned a value 0. The word double A is assigned a value 1. The word triple A is assigned a value 2. And likewise so on. So we printed only first 100 words and their indexes. And again, we have printed any word. Here we choose the word government. We can choose any other word also from our vocabulary. So here we have printed the index for that word, at what index is provided to this word. So the index of the word is 15,415, and we have also printed the one-hot encoded vector for that word, which is a vector which contains 0 at every place except a vector with 1,050 entry. Here the entry will be 1. So after generating one-hot encoded vector for each word in the vocabulary and defining our vocabulary, now we generate the pairs, the context and target pair for both the models. First, we will generate it for SIBO model. So here, what we did is we start by choosing a sentence here the sentence is user defined. You can take any other sentence also. I have chosen it as 5. You can take it any sentence, any index. So we have chosen a sentence whose index is 5 for the processing. Now here we define two variables, x which store the context variable and the variable y which store the target variable. Now what we did in this step is for any sentence I, we define the context window size, like how the context and target pair is created. So context is created is the sentence minus the window size. This window size is dependent on our choice. We can choose it like any number, whatever we required for our purpose. So the context size is defined as sentence plus the sentence part. The sentence ith word at the sentence minus window size plus the ith word at the sentence plus the window size. And the target is the sentence is the ith word of the sentence. That is the center is the target. And this part will choose the left word of the target words, and this part will choose the right word from the target words. So here we have created here we have defined context and target, like how context and target are created. So now in here we have defined we have defined all the context and target pair for every word in sentences, and we have stored them as the sentence I with the sentence label. At last, we convert the word into the context and target word into their corresponding index from vocabulary. This goes into our training set X and Y. The context in the target word which we have created here will go in our training data as like we have created above as X and Y. Now we will generate the context and target pair for every sentence that's in our pre-processed data set. Here in this command, we have generated the context and target pair for the SIBO model for the entire data set. Now, how does this context and target pair look like? Here generated in this command, what we have done is we have generated context and target pair for all the sentences. Like in the above command, we have generated the context and target pair for all the word in a particular sentence. And here we have generated for all the sentences. So now how this context and target pair look like for this, we will print the context and target pair. Here we have choose our sentence index to be 5. So you can choose any other index also. If the index is in the vocabulary, then definitely it will process the further part of the code. If no, then it will show that no valid SIBO pair found for the chosen sentence index and try another one. So how we have chosen, as we have chosen the sentence index 5. So here is our output look like as. So this is our original sentence whose index is S5. It is recommended that Fulton legislator acts to have these laws studied and revised to the end of modernization and improving them. So we have defined here our target word and context word. We have already defined our window size here as 2, and we have chosen our target word as the 5th word. So how these vectors look like that? Our target word is the word act, and as our window size is defined as 2, so these 2 words on the left will serve as the context for this word target word act, and these 2 words on the right will also serve as the context for the target word act. So this is how it can be interpreted as, like, the context words are these 4 words and our target word is the word act. So this is how the context and target pair look like for SIBO model. Now we generate our context and target pair for skip-gram model. So here we have chosen the same sentence. We have chosen the same window size 2. We have defined 2 variables, x and y. The x variable hold the target word. The y variable will hold.
Hello? Hello? Pooja? Hello? Rinki? Am I audible?
Yes, sir, you are audible.
Okay, okay. No, I mean,
So
I could not listen. Yes, yes.
am I audible to all?
Yes, now you are audible for the 10 seconds. I could not hear you.
Oh, okay, sir.
No problem. Now it is clear. Yeah, please go ahead.
So should I repeat or?
No, I think for me, I think that was a problem. For others, I think it is okay. So you just continue.
Okay, okay. So participants, if you have any problem in network connectivity, please let us know. So continue by generating the context target pair for skip-gram model. Here we have defined loop over each sentences this is how we generate the context and target pair for skipgram model. Here, our target is to predict the center word, and given the context word are the neighboring word. Depending on the window size, we can choose the neighboring words. So here we have defined how our context and target word are defined. So for any target word, so for any sentence we will construct the context and target pair and store them in the list X and Y. And for every sentence in the data set that we have pre-processed, we have stored our skipgram generating pair in the variable X, SG, X, Y, XG, and the sentence reference. So here also again we can see how the skipgram pairs look like. So here again, as I have chosen the syntax index 5, so we will print all the skipgram pairs for our defined size for the sentence index 5. So this is how the output look like. This is our original sentence which has index 5. As we have defined our window size to example look like, suppose this is the first word, the target word is it. So as our window size is 2 and there is no word on the left side of it, so definitely there is no neighboring word on the left side, but we can have its context on the right side. The first word is recommended. Similarly, as our window size is 2, so the second word which serves as context for the word target word it is that. Similarly, if our target word shifts to the second word recommended, so here on the left side we are having one word, so the context word is it for this, and also on the right side we have that and gluten that serve as the context word for the target word recommended. Similarly, if we shift to the third word, that is that, we can again see it, recommended, fluton, legislator. All these 4 words serves as the context word for the target word that. So this is how the skipgram model pairs look like. After generating the context target pair for both the models, SIBO and skipgram, we now come to the training part of these models. How? So first we will see the training of SIBO model. Here we have imported all the necessary libraries. We will shift our device to GPU if it is available. So here we have defined the SIBO model. This part defines our SIBO model. The forward layer, as in SIBO model, we can see that we are having context data as our reference data, and we want to predict our target data, that is the center word lies between the context. So our we are having more than one word in our input. So what does this forward layer do? This forward layer means the average, the embedding of all the context words. Suppose we are having 4 words in our context data. So for every word, we are having an embedding. So this forward function will take the average of all the 4 words embedding. And then what it will do, it will pass it to the embedding layer of the SIBO model. And after passing through this embedding layer, the output of this embedding layer will pass to this linear layer, and this linear layer will project the output on a vector that is of the dimension of our vocabulary size, in order to see that which word is most likely to appear as our target word. So this is how we define our SIBO model. Here we have defined our training data as a tensor, which are stored as X tensor and Y tensor. So we defined our embedding dimension as 50 for better learning or As per your choice, you can take it as any other value. The loss function is defined as cross entropy loss. Here we have run this model for 30 epochs. So this is how the training look like, and we print the epoch and loss respectively. So this is the output for the training of SIBO model. As we have run the code for only 30 epochs, you can run it for number of epochs you can increase as per your choice, as per your task. So after the training of the SIBO model, we save the SIBO model for further testing. So this is how we save our fully trained SIBO model. The SIBO model is shown at SIBOmodel.path. Now we come to the training of the skipgram model. So here we have again imported all the required libraries, and also we check the availability of the GPU if we have. So after this, we define our skipgram model. So in skipgram model, we have our target word, we have our context word is the center word, and we want to predict the context for them. So here the difference is that as our input is a single word, that is the center word, which is our context word, and we want to predict the target word is the neighboring word of that word. So we want to predict more than one word. So here the difference is that we have no need to take any average, as our input is only a single embedding, single word embedding. So here we can see that this forward function passes the embedding layer, passes the embedding of the input word to the embedding layer of the skipgram model, and that the output of this embedding layer will pass to the output layer of the skipgram model, which will project the input on a vector of size, vocabulary size, to check to find out which word are the context word for the given word. So this is how the skipgram model is defined. So here we have created our text trained data. So again, I took the embedding dimension as 50. You can increase it as per your requirement. The loss function is cross entropy loss. The optimizer is Adam. So as skipgram is heavy to learn, sir has already shown in the code. So here we run the code for 20 epochs only. You can run it for number. You can increase the number of epochs as per your choice. So the output is printed as these are the training loss for 20 epochs. So after the training,
Pooja, I'm not able to hear. Am I audible? Pinky? Hello? Pooja? Pooja? Hello? Hello? Pooja, you are not audible. Hello? Rinky? Hello? Rinky? Pooja? Am I audible? Yeah, your voice just stopped. Hello?
Yes, sir, yes, sir. So, sir, now am I audible?
Yes, yeah. Now you
Hello.
are audible. Yes, now audible.
Okay, okay, sir. So, after training of Kiram model, we train skill. So, as this is an unsupervised learning, so how do we know that the model is or the question? So, for this, how our model is learning things. Here, how we have extracted embedding for the fully trained model, like how the embeddings look like. So as we have defined our embedding dimension to 50, I have chosen some words like government, school, money, connect. Depending on your vocabulary, as these words are very common words frequently occur in each data set. So I have chosen these words. So I have printed the embedding that is learned by the SIBO model for these 5 words. Here I have used the, I have extracted the embeddings that the SIBO model learns. So the word map is represented is model. So therefore these words have model. These words are the script model of XML model embedded.
Pooja, your voice is breaking. Hello? Pooja? Hello? Voice is breaking, Pooja. Voice is breaking. Hello? Yes, but your voice is breaking. Your voice is not clear. It is breaking. Hello?
Yes, sir. Actually,
Your
yes, sir.
voice is
Actually, there
breaking.
is a done electricity. Hello.
Hello? Yes,
Hello,
yes.
sir. Am I audible now?
Yes. Now you are audible. In between, sometimes the voice breaks.
Actually, sir, there is a electricity, so that's why the connection lost. So, is it fine now?
Yes, it is fine. Yes.
Okay, okay. So, In the above code, what we have done is, after the fully trained SIBO and skipgram model, we want to see how the embedding look like. So we choose some frequently occurring words in the vocabulary. So you can choose these words of your choice, and we printed learned embedding for these words using how the embedding look like. Now we come to the use case, like how can we check whether our model is learning the things properly or not. So we come to a use case scenario. Here what I have considered is we predict the closest word for any word by calculating the cosine similarity of a given word. Like what I will do is I will provide the code is as follows. I will explain the code step by step. Here we have imported all the necessary libraries. We have loaded our fully trained model that we have saved for eval. Here we have activated these models for the evaluation part. Transfer these models to the device on which device we are working, either CPU or GPU. So what this code will do is it will ask us to enter a word that is in your vocabulary. If the entered word is in the vocabulary, then it will process it further. If not, then the output will be printed as that the word is not in the vocabulary. So if the word is in the vocabulary, what the code will do is it will find what I want to do for this is that it will predict the closest word for the given word. So I have printed three words here. Here I have considered top three words. This how is this how will this find how will the model find the closest word? The model will find the closest word by calculating the cosine similarity. That we have already discussed in the morning lectures how the cosine similarity is calculated. So this is the code for the SIBO model to find the closest word for the given word. And here this is the code for the skipgram model to find the three closest word for a given word. So when we run this code, how the output look like? It will ask us to enter a word. So suppose I have entered a word girl. So the top three words using the SIBO embedding is man, boy, or woman. These are the words. Actually, we have, as our embedding dimension is also less, we have taken our embedding dimension as 50, and also we run our model only for 30 epochs. So if we increase our embedding dimension, or if we increase our number of epochs, so the results will definitely get better. And this is how we can evaluate the performance of our model. Similarly, the top three words for skipgram are these, which are not relevant just because of the training of the model. If we will train the model on a large corpus with fine-tuned hyperparameters and for increased number of epochs, definitely we will get better output. Our model will learn better embeddings for the words in the vocabulary. So this is the use case. What we will do in this notebook is first we use ground purpose construct our model, then the architecture from scratch. We train our model and then we evaluate how the model performance can be evaluated. So we have seen a use case for that scenario. So is there any doubt in this? if you are having any doubt, you can ask.
Please let us know if you have any doubts. The participant, please let us know.
So, sir, should we proceed with the second use case?
Yes, you can proceed, Pooja.
Oh, okay. So, so like we have already seen of probably prediction of the loss using Seaborg's gram model. There is analysis. Not and what we have done is we use IMDb dataset, not movies consists of 50,000 movies review. This is a balanced data set. Consists 25,000 positive movie review and 25,000 negative movie review. So what we have done in this notebook is we start by pre-processing our data. Then we train our SIBO and skipgram model on the training data, and then we have evaluated their performance on the test data. So let us start with the notebook. So here we have installed all our required libraries. So after importing all our required libraries, we have import all the necessary libraries that we use in this notebook, like Torch or Seaborn, Pandas, Genzim. All these libraries, we have imported all the necessary libraries. Here we have transferred our model to use GPU if available. So now we come to the pre-processing part of the dataset. So we are using IMDb movies review dataset. So here we have imported our IMDb movies review dataset from kiraz.dataset, import IMDb. Now we have constructed our dataset pair as X full as Y full. The X full is considering the review of the movie, and the Y full is the corresponding label for that review, which is either positive or negative. So this is how we construct tuple for the review and the label for a given review. So now we manually split our data set for the training data set and testing data set. So we have split our data set as 80% of the part that we will use for the training and 20% we will use for the testing part. So this is how we define our train data and test data. Now we will define our word index. So as we have already defined in the last code, here also we will define our word index. Here we start our word index with 3 as 0, 1 and 2 are already reserved for head, padding, start and unknown sentences. So as in the last code we have started our indexing from 0. Here we have started from 3. So now after pre-processing the data and splitting the data into training and testing part, we will see how our data look like. So we have printed our training samples for 10 samples say, and here we have printed our testing samples. Here also we printed the 10 samples. So this is how our data look like. This is the training sample. This is the first review. And its corresponding label as negative. This is the second review and its corresponding label as positive. So these are the 10 reviews that we have printed for the training data. Similarly, we have printed the testing data. Here also we printed the 10 reviews with their corresponding labels. So after the data pre-processing and defining training data and test data, now we'll build it. In the last code, we have defined the hyperparameters of our choice. The embedding dimensions as 50, the number of epochs as 20 and 30 for the skip gram and SIBO model respectively. Here we have used hyperparameter tuning. As we have already discussed hyperparameter tuning. So here how this code look like is we have imported all our necessary libraries, checking whether the GPU is available or not. Now we tokenize our data. We tokenize our data as a review, as in lowercase data, which is a train data. So here what we did is to generate our vocabulary, we introduce a minimum threshold for a word to be included in our vocabulary. Like in our data, there are many words which will occur very less time. Rare words, we can say very rare words. So what we did is we set a minimum frequency count of 5. That is, if a word has occurred in our data more than 5 or equal to 5 times, then it will be included in our vocabulary. So this is how we define our vocabulary. So after defining our vocabulary, these are the functions, word to index mapping and the reverse function index to word mapping that we have already discussed. So we have, as we have already discussed, that we have 50,000 movies review. So after applying thresholding to the vocabulary size, we print our vocabulary size like this. Now we generate the training pair of SIBO model. So this is how the training pair of the SIBO model is generated. We generate the context word around the target word, like and the center word is our target word. So this is how we have already seen that this is how we can generate our SIBO context and target pairs. And now we define our SIBO model. So this is a SIBO model we have defined here. Here we have, in this part, we have converted all the context word and the target word into the tensors using the word to index map, as our system understands only embedding. So we have converted the words into the tensors. Now, what we did is we start with the training process. So this is how the SIBO models look defined, the embedding layer and the linear layer that we have defined in the last code. This is how we have defined our weight initialization technique. So here we chose Xavier's technique. to initialize our weight. This is the forward layer that did the average of all the embeddings in the context word to predict the target word. So this is the forward layer for the SIBO model. For hyperparameter tuning, here we are having 4 hyperparameters that we are considering: the embedding dimension, the context size, the batch size, the learning rate. So for hyperparameter tuning, we are using grid search method. So in that method, we will provide some choices to our model, and our model will cross check over all these choices and evaluate the model performance. So the number of trials we have defined as 5. Like choose pairs from these defined what we can say is range for this hyperparameter, and trial. This is a trial epoch. Trial one epoch over chosen choice of hyperparameters and calculate the loss. So this is how the hyperparameter tuning works here. So now after defining our hyperparameter tuning, we have defined the hyperparameter search as that this is our embedding dimension. What embedding dimension we are choosing from the grid? This is a variable. So now after defining all the hyperparameters and after generating all the context and target pairs, we initialize our SIBO model for the training. Here the SIBO model is initialized for the training. The loss function is again the cross entropy function. The optimizer is the Adam optimizer we choose as in the last case. And this is the whole training loop look like. So we print our loss, and the output for this model look like this. What this is, as we are using hyperparameter tuning. So this is our first trial. We choose our embedding dimension to be 128, our context size to be 1, that is the window size to be 1, the batch size to be 64, learning rate to be 0.001. And as we have ran our model only for one epoch, in case of hyperparameter searching, hyperparameter tuning, so this is the average loss. So for all the trial, the model compute the loss, and once the model reach to the best hyperparameter, these are the chosen best hyperparameter. So now our train, we train. We have designed our model for 3 epochs, as you can run it for more than 3 epochs according to your task. So this is how the training of the SIBO model done for the IMBD movie reviews dataset. And after training, we save our fully trained SIBO model like this. We will use this model further for the inference part. Similarly, we did the training of the skipgram model using hyperparameter tuning. This is how the code look like. First, we have imported all our necessary libraries. Similarly, we check for the available device, whether CPU or GPU. Now we tokenize our data by converting all the data into lowercase data. Here also we define our vocabulary as applying by a minimum threshold count, which is 5. So here also we generate our vocabulary as those words only for which the word count is greater than or equals to the minimum frequency, which we set as 5. These are the famous functions that assign what we can say a numerical identity to a word. So word to ix and ix to word. These two functions, the first function assign index, a numerical quantity to a given word. The second function is the reverse word. This word will assign a word given a numerical quantity. So similarly, we will print our vocabulary size after setting the thresholding. Now we define a training, context and target pair for skipgram model. So we have created, we have already seen how to create the context target pair for skipgram model. So this part deals with that, how the context pair and the target pair are created in case of skipgram. Now we will call our skipgram model here. So this is how our skipgram model is defined: one embedding layer, one linear layer, and a forward layer. The forward layer is here. The forward layer is not using the average function. Again, the reason is that as the input is only a single word, so there is no need to do average as we are doing it in case of SIBO. So this is how the skipgram model defined: the embedding layer followed by the linear layer, which projects the output of the embedding layer into a vector whose dimension is our vocabulary size. So here we use the again Xavier weight initialization technique. This is our grid search for the hyperparameters. Here we also use 5 trials and 1 epoch. That this epoch will, what can I say? This epoch will show the loss for a particular choice of these hyperparameters. So after defining all the hyperparameters, like we have defined these for our hyperparameters, we print our output as, here we have defined the training loop using the loss function, the optimizer. So the the output for this code look like as this is our vocabulary size after thresholding, and we start with the choice of dimension embedding to be 128, context to be 1, batch size to be 64, learning rate to be 0.001, and the computed average loss is 6.62. So similarly, the model will check for all the possible combinations of these hyperparameter choices and compute the loss for one epoch only, as we have defined for one. We can increase the number of epochs, but it will increase our computational complexity. So for that, to tackle with that, we choose here the number of epochs to be 1. These are the best hyperparameter that model find from the available range of hyperparameters. We retrain our model. Again, I have retrained it for 3 epochs only, as if you want to increase your accuracy, or you are training your model for a task which is which require very high precision, you can increase the number of epochs. So after the training of the skipgram model, we save our skipgram model is as follows: that we have saved our SIBO model. So this is how we saved our skipgram model. Now, after the training of these two models, we have to evaluate the performance of the model. So the last case we have seen is the predicting of the closest word, as now we are using the data of new movies review. So what we are doing is we are evaluating our trained SIBO model and skipgram model on the test data of the movies review dataset. So here what we have done is we load both the models, the SIBO model, the fully trained SIBO model, the embedding weights of the SIBO model, and the skipgram model, the fully trained skipgram model that we have saved for our further inferences. So we have loaded that both the fully trained models, and what we did is we choose 3 random samples from the test data. Here we choose 3 random samples of movies review from the test data, and we try to predict the output for the chosen 3 samples using the SIBO model and skipgram model just in order to evaluate the accuracy of these two models or the performance of these two models, we can say. So here we have selected 3 samples. So what we are doing is we are predicting the 3 random samples using SIBO model and using skipgram model. We have also printed the ground truth or the label that is in the test data for the chosen samples. So here the prediction is making using SIBO model and the prediction is making using skipgram model. So this is the output look like. These are the 3 random samples from the test data. This is the first review. The ground truth is negative. The SIBO model prediction is also negative, and skipgram is also predicting the review as a negative review. Similarly, for the second review, this ground truth is negative, which is same as predicted by the SIBO model and skipgram model. Similarly, for the third review, the ground truth is positive, but both the model are predicting it negative. So if we want to, this scenario shows that the model is learning things. So as we cannot evaluate the test accuracy. So this is how we can check whether our model is learning things properly or not. So here, if we increase the number of epochs or if we will go with any further technique for hyperparameter tuning or something else, we can increase the accuracy as per our demand, as per our task. So, but this is how the use case of the embeddings learned by these two models. The last one we have seen is the prediction of the closest word by calculating the cosine similarity. In this notebook, we have seen the sentiment analysis. The model are classifying the reviews as positive or negative on the basis of their learned embeddings. So, is there any doubt in both of these two scenarios that we have discussed?
Participants, any doubts? We'll share this all the notebooks on your portal, and you can access and you can learn. And if you have any doubts, you can further ask through. Pooja, so now we can conclude.
Yes, sir. If anyone is having doubt, then we can take. Otherwise, we can
Yes,
conclude.
yes. Yeah, so